Hello, and welcome to our screencast on the history of the modern periodic table. We're going to start, as we start all lessons, with a retrieval practice. So I'd like you to read through the questions, pause the video, and come back when you've answered the questions. Okay, welcome back. What are the missing labels A and B on the model? And what is the name of the model? Well, A is a cloud of positive charge. B are electrons, and the model name is the plum pudding model. Why do atoms have no overall charge? Well, there are two things to take into account here. Okay, number one, you have to say the size and the type of charge on the proton. So it is +1. And the charge on the electron is equal and opposite in size, -1. You also have to say that there's an equal number of protons and electrons in an atom. What was the role of Niels Bohr in the development of the model of the atom? Well, Niels Bohr, he suggested that the electrons, instead of just being somewhere outside the nucleus, are actually found in shells or energy levels, and each one of those shells is a fixed distance from the nucleus. What is the atomic and mass number of this atom? Now, in order to find the atomic number, you have to count the number of positive charges, the protons, in the nucleus. And in order to calculate the mass number, it's the total number of particles of protons and neutrons. So as you can see, we have 2 positive charges, so the atomic number is 2. And we have 4 particles in all, so the mass number is 4. Okay, so this is our success criteria for today. We want to be able to identify elements from their group and their period number. So we're going to look at the periodic table and make sure we can do that. You want to be able to describe the steps in the development of the modern periodic table. And we want to look in depth at what Mendeleev did in order to get it very close to what the periodic table looks like now. Okay, so this is a recap of what the modern periodic table looks like. You get a copy of this in your examination. The elements are ordered in order of atomic number, which is the number of protons. Now, protons go up in ones because you can't have half a proton. So we start with hydrogen here, which has 1 proton. Then we go to helium that has 2, lithium is 3, etc. Okay, and we've got up to well over 100 elements in the periodic table. Now, the elements are ordered so that they fall into what we call groups. The groups are columns as they go down the periodic table. There are 8 groups, and the numbers of the groups are at the top. 1, 2, 3, 4, 5, 6, 7, and then group 0. So there are 8 groups in the periodic table. The first one we need to study in detail is the alkali metals. Then we've got group 2, group 3, group 4, group 5, group 6, group 7, which we need to look in more detail, and group 0, which we also have to look at. Okay, now what do they tell us? Well, they tell us how many electrons are in the outer shell of that element. So, for instance, all of group 7 have 7 electrons in their outer shell, and all of group 1 have 1 electron in their outer shell. Okay, the other part of the periodic table that we don't have to really study is the middle block. They're all metals and they're called the transition metals. Right, let's look at the rows in the periodic table. The rows in the periodic table are called periods. Okay, so we've got period 1, period 2, period 3, period 4, period 5. Okay, I haven't gone any further because there is a missing group in the next 2 periods that have been taken out, and often you see them separate, right? But that would be the 6th and 7th period. Now, what do they tell us? Well, they tell us how many shells that the element has. So the periodic table is actually quite a powerful tool to actually tell you all about an element. If you look at each of the elements, from the atomic number, you can tell how many protons you've got, how many electrons you've got. From the mass number, if you take the atomic number away from the mass number, you've got the number of neutrons. You know what the element is called. You know how many electrons are in the outer shell from the group, and you know how many shells that the element has from the period. Okay, so what I want you to do is just look at this periodic table and pause the video now and quickly jot down which of those elements would answer question A to E. Okay, welcome back. The element that is an alkali metal is in group 1, so that is sodium. The element that is a transition metal, so remember the transition metals are in the middle, so that is copper. The element in group 4, so that will be below the number 4, is carbon. And the element with a full outer shell of electrons has to be in group 0, so that is helium. And the other element that goes in the shaded box, that's the only one that's floating on its own, and that is hydrogen. Okay, so hopefully now you're able to identify elements from knowing which group they're in and where they are in the periodic table. Okay, so let's look at our second success criteria, being able to describe the steps in the development of the modern periodic table. Now, when we first started, there were less than 50 elements that had been discovered. Scientists did their best to try and organise these elements based upon similar properties. But it was very difficult, and it wasn't very accurate for all the elements. It had massive flaws. That means lots of mistakes. So why do you think there were lots of mistakes in their first attempts? Right, it was flawed because there weren't enough elements for them to do it properly. They needed more elements to get more data and to be able to do it properly. Okay, a scientist called John Newlands came along, and he made a big attempt at trying to do a periodic table. This is one of the earliest periodic tables. He arranged them in order of atomic weight. He noticed that every 8th element had similar properties and developed a table based upon that. He called it the law of octaves, which means 8. Now here is his early attempt at a periodic table. What I want you to do is pause the video and try and answer these 2 questions. Okay, welcome back. So why were the elements not arranged in order of atomic number? Now, in order to be able to answer that question, you have to fully know what atomic number means. So it means the number of protons. Well, it wasn't ordered in the number of protons because protons hadn't been discovered at this time. Why should you not put hydrogen into group 1? So think about what group 1 is like. What are the elements in group 1 like? Well, they're all metals, and they're all very reactive metals. What's hydrogen like? Well, hydrogen is a gas, so it doesn't fit in with a pattern, does it? So group 1 is normally very reactive metals, and hydrogen is a non-metal. Okay, so what problems are there with Newland's table? So if you look at that, you can see various things. Okay, you can see metals and non-metals in the same group. You can see various places where they in fact put two different elements in the same group. You can see groups that have reactive metals and non-reactive metals in the same group. So what he was trying to do was basically force a periodic table with very limited data and say it was correct. So it's incomplete, first of all. There's so many elements not being discovered. There are no group 0 elements. Many elements hadn't been discovered, and he left no gaps for them to be placed because he was just basing it on what he knew. The elements in groups don't have similar properties. For example, oxygen and iron, non-metal and metal, or sodium and copper, reactive metal and unreactive metal. And you've got many examples of metals and non-metals mixed together. Now, at a scientific meeting, because you've always got to do peer research, and they came up with the statement that if he'd actually done it in alphabetical order, it would have made just as much sense. That's a real put down. That's a real sort of insult. So we had to put up with that until this Russian scientist came along, Dmitri Mendeleev. Right? He was a Russian chemist. In 1869, he solved the problem and developed the basis for the modern day periodic table. It's not exactly what it is today, but he did do things that we could build on. He arranged them in the same way that Newland's did, with atomic weight, and so that a periodic pattern could be seen in the properties. He was really trying to put them in groups where they were similar properties. Okay, so this is an example of an early periodic table that he developed. It's still got flaws. You might notice that there are still some places where he has got gaps, some places where he might have put lots of elements in the same box. But what he did do was he did sort of say, well, there will be new elements to discover in the future. Okay, so he still put them in order of atomic weight. He did put them in groups. But what he did, which Newland's didn't do, was he left gaps for undiscovered elements. What he also did was he predicted the properties of those elements. And when they did discover it, they found that he was spot on with all of the properties. The other thing that he did, which when you're doing a paper, you often forget that he did, is he swapped the order of some of the pairs of elements, which we'll talk about a bit later on. So he was more fixated on putting them in the correct group than putting them in a correct order of atomic weight. Okay, so what I want you to do is look at Mendeleev's table, okay, which is this one, and look at Newland's periodic table and say, what sort of improvements did he make in comparison to Newland's? But what limitations does it still have? So what things could still be improved? Please, could you pause the video now, answer the question, then come back when you've answered. Welcome back. Hopefully you managed to do that. So what improvements did he make in comparison to Newland's table? Well, the improvements he made is he did realise that there were elements that had not yet been discovered. He left gaps for those elements, and it looks a little bit more like our present periodic table in terms of groups. What limitations does it still have? Well, the noble gases are still missing. There are still some boxes that have more than one element in it, And he did try to put the transition elements into groups with the other elements. Okay, now at this point, I'd like you to pause the video, copy the YouTube link above, watch that video, and then come back and answer the questions before you resume the screencast, please. Okay, hopefully you enjoyed that video and you've managed to answer the questions. So let's go through them now. What year was one of the first versions of the periodic table put together? Well, that was 1870. What did Mendeleev do, which was pure genius? He left gaps in his version of the periodic table because he presumed that the elements hadn't been discovered yet. Based on the location of that unknown element, he was able to predict a lot of their properties. What is the atomic weight of aluminium? Aluminium has an atomic weight of 68. What properties did he predict for aluminium? Well, he said it would be a solid metal at room temperature, malleable and ductile. It would have a melting point which he described as freakishly low for a metal and has a density of about 6 grams per centimetre cubed. When it was discovered, what was it called? Well, it was called gallium, and its properties matched very closely to what Mendeleev said. It had a mass number of 69.72. It did conduct heat. It was malleable and ductile, and its melting point was, as Mendeleev said, freakishly low at 30 degrees, so that it could melt in your hand. How did the properties match Mendeleev's predictions? All of them matched. What are some of the other names of elements that Mendeleev predicted existed? Some of the other elements are scandium, germanium, and rhenium. Okay, so that concludes our second success criteria. If you still don't understand, then pause the video and rewind it and come back when you have a little bit better understanding. Okay, we're going to look at our third success criteria. We're going to look at those steps taken by Mendeleev to arrange the elements a lot better than his predecessors did in proper groups. Okay, so he left gaps. I think this is one of the things that you do remember, right? He left gaps for those elements that had not been discovered, and he predicted the properties. And those properties matched. Okay, when these elements were discovered, they closely matched his prediction. Okay, so Mendeleev still ordered the elements with their atomic mass or atomic weight. So some of the elements didn't fit with Mendeleev's pattern. For example, argon has a higher mass than potassium. And that means that argon would ordinarily in his table fall under group 1 and be a reactive alkali metal. Tellurium has a higher mass than iodine, which would mean that tellurium would end up in group 7, but it doesn't have those properties of group 7. Okay, so Mendeleev said that certain exceptions should be made. The elements with similar properties should still remain in the same group, so he swapped their places, and we're going to look at that on the next table. Okay, so what I want you to do is try and remember what I've just said, and why did he swap tellurium and iodine? And if you look at tellurium and iodine now, right, iodine has a mass of 127, whereas tellurium has a mass of 128. So they should be the other way around if you were going by atomic mass. Why are argon and potassium not ordered by atomic mass? If you look at argon there, it's 40 and potassium is 39. So argon should be down there and potassium over there. So why did he swap them? Pause the video now and try and explain. Okay, welcome back. Why did Mendeleev swap tellurium and iodine so that they were not ordered by mass number? So if you look at tellurium has a mass of 128, whereas iodine has a mass of 127. So really, tellurium should be in with the group 7 elements. Okay, so he thought iodine fitted better with those properties of group 7, so he swapped them round. So he swapped it so that iodine could be put with the group 7 halogens. If you look at argon and potassium, argon has a mass of 40, whereas potassium has a mass of 39. So really, argon should be down with the group 1 elements and potassium would be up here. So he swapped them round so that potassium could be put with the group 1 metals. Okay, so argon and potassium, those are two that he swapped, and tellurium and iodine. Okay, the modern day periodic table, once we started to discover things about the structure of the atom like protons and neutrons and discovered many more elements, we were able to put together a more accurate periodic table. It was quite clear that Mendeleev's periodic table accommodated for patterns in atomic structure, and this allowed scientists to continue to develop his periodic table into the periodic table we know today. The periodic table now is ordered by atomic number, proton. Now the reason for that is because every element has isotopes, and isotopes can influence whether or not its relative atomic mass is higher or lower than the previous one. Okay, so that would account for why argon and potassium and tellurium and iodine needed to be swapped around. Okay, so what I want you to do now, we're going to have an exam style question. This is the sort of thing that you get with 6-mark questions. I want you to evaluate Newland and Mendeleev's tables and do a comparison between them. Now, you want to say what are the good points and what are the bad points. What did they do the same? What did they do differently? And then come to a valid conclusion at the end of why Mendeleev's was more acceptable going forward. Right, pause the video now and come back when you've answered the question. Okay, hopefully you had some success with that. Right, so let's have a look at the answer that the exam board gave. Okay, so comparative points, so things that they both do the same. They both have more than one element in some of the boxes. They both have similar elements in the same column. Both are missing the noble gases. Both arrange the elements in order of atomic weight. Right, advantages of Mendeleev or disadvantages of Newland's. Newland's didn't leave any gaps, but Mendeleev did. Newland's had many more dissimilar elements in a column. That means there were more that didn't match. Mendeleev left gaps, and Mendeleev changed the order of some of the elements like tellurium and iodine, argon and potassium. So the points which led to the acceptance of Mendeleev's table, well, Mendeleev predicted properties of missing elements. The elements with the properties predicted by Mendeleev were discovered, and Mendeleev's predictions turned out to be correct, and the elements that were discovered fitted in the gaps. Okay, so if you were doing something like that, comparing them, writing either the advantages or disadvantages of Mendeleev or Newland's, and then came to a conclusion of why Mendeleev's was better, you would be very successful in that exam question. Okay, so that concludes the screencast. Hopefully you understand a little bit more about the development of the periodic table.